All right, so moving on here to some of the problems here related to specific heat capacity. But quick, before we do the example problem, let's just evaluate this equation a little bit. So if we look at this equation, there's four different variables in this equation. There's the specific heat capacity, there's the amount of heat transferred, there's the mass of the sample, and there's the change in temperature. The way we're going to use this equation is going to be a little different than a lot of the problem solving we've done so far. We're not going to necessarily be canceling out units to figure out how to get to the answer. We're really going to be applying this equation. So this will be a little bit similar to calculating the density, where you've got to take the constituent pieces of information like the mass and the volume and putting them together in the right fashion. That'll, in a lot of cases, is what we're going to need to do here. But just looking at the equation, we should anticipate at least four different potential questions. One could be what's the specific heat capacity, one could be what's the heat, one could be what's the mass, one could be what's the temperature change, or something related to what's the temperature change, such as what's the temperature going to be after this much heat is added. So you should be prepared for all four of those equations, and you could derive a formula that addresses each one just by rearranging this equation here based on the definition of specific heat capacity. Okay, let's look at the example here. So, in an experiment, it was determined that 59.8 joules, so there's our heat right there, that's transferred, was required to raise the temperature of 25 grams, that's a mass, of ethylene glycol by 1.00 degrees C. Right? And that's how much the temperature went up. So that is the change in temperature, or delta T. We're asked to calculate the specific heat capacity. So in this case, we're using the exact formula we have up here. The specific heat capacity is going to be equal to the quantity of heat divided by the mass and the temperature change. So we just plug those variables in the right places. 59.8 joules divided by 25.0 grams, right? And then also on the bottom is going to be 1.00 degrees Celsius. Right now, putting that 1 on the bottom, mathematically that doesn't do a whole lot, but it is important that we get the units in the right place, because if the temperature change isn't 1, it's certainly better be on the bottom of your fraction when you do that calculation. Now, unit-wise here, joules on top, grams degrees C on bottom. Nothing cancels out, but that's good because those are the units we want to describe heat capacity, joules per gram degrees Celsius. So we just have to punch in the numbers here, 59.8 divided by 25. Right? And we don't have to divide by 1. So that gives me 2.392. Everything that went in there is 3 sig figs, so my answer should also be 3 sig figs. So 2.39 joules per gram degree C would be the specific heat capacity of ethylene glycol here in the problem. Okay, let's look at a couple other examples I mentioned. Right, you can have several different problems based on that equation, so let's look at another possible problem here. So at the top of the second page there, we want to calculate the amount of heat required to raise the temperature of a 45 kilogram sample of ethanol from 11.0 to 19.0 degrees C. And then at the end, we're given the specific heat capacity of that material, 2.42 joules per gram degree C. So in this case, what's missing here is heat. So maybe a good place to start here would be to think about, well, how could we get an equation that we can solve for heat? So if we take that equation we talked about in the last problem, if I multiply both sides by the mass, I'll cancel it out on the right, it'll show up on the left. Multiply both sides by temperature change, it'll cancel out on the right, it'll show up on the left. I would end up with this equation. Specific heat capacity times the mass times the temperature change is equal to the heat. Okay. Excuse me. Alright, so if we're solving for the heat, all we need to do is get those 3 pieces of information, put them into the problem correctly. Now, this problem, things are slightly more complicated than that. So keep in mind the units on specific heat capacity, joules per gram degree C. That means grams is the unit we want for our mass. So this 45 kilograms, we really want that to be in grams if we're going to plug in and cancel out units with our specific heat capacity units. So let's change that to grams. There's 1,000 grams in a kilogram. and that would be 45,000 grams. Right? Temperature change, we're also going to have to figure out on our own here. If the temperature starts at 11 and goes up to 19, that is 19.0 minus 11.0. 8.0 degrees C is our temperature change. Okay? So the standard way to calculate temperature change is the final temperature minus the initial. Right? We'll talk about when that's negative and how we can deal with that, right, when we encounter that not too far into the future. Okay, so if our mass is 45,000 grams, our temperature change is 8 degrees C, and we know the specific heat capacity because it was given in the problem. Then the heat is going to be equal to that specific heat capacity times the mass times the temperature change. And I'm writing out all the units here because some of them do cancel out in this particular equation, right? Because we're multiplying the specific heat capacity by mass. The grams on the bottom of the specific heat capacity will cancel with grams on the top of the mass, or just there in the mass. And the same is true for degrees C with the temperature change. And that means we'll just have heat units left. And that should make sense because we're trying to calculate the quantity of heat. So we just need to multiply here. 2.42 times 45,000 times 8. And because of our temperature change, we drop down to 2 significant figures here, so we really only want 2 significant figures in this answer. Now on the calculator, it's 871,200, and that means I can keep the 8 and the 7. So when I round this to the right number of significant figures, it would be 870,000 joules. Now, 870,000 is a big number, so it would be a little more common to refer to that as 870 kilojoules for our final answer there. Although it just says heat in this case, so either answer would be acceptable. Okay, now let's look at another version. Here we've got an iron nail. We're given the mass, 12 grams. We're given the quantity of heat it absorbs, 15 joules. And we're told if the nail was initially at 28 degrees C, what is the final temperature? Okay, so if we don't know what the final temperature is, that means what we're trying to solve for here is delta T. So we want to find delta T. Now the problem isn't quite over when we find delta T, because we'll have to figure out, right, starting from this temperature and applying that delta T, what is the new temperature. So in this case, what we have is mass, heat, and specific heat capacity. So again, in fact, this time let's start with this equation. Specific heat capacity times mass times delta T is equal to Q. So if you do feel more comfortable memorizing an equation here instead of just trying to figure it out from maybe the way the units relate, this is probably the easiest one to remember because there's no fraction. This is also going to be the easiest one to then manipulate. If we're trying to solve for delta T, all we need to do is move the specific heat capacity and the mass back to this side of the equation. So dividing both sides by specific heat capacity and mass would be delta T equals the quantity of heat divided by the specific heat capacity and the mass. Okay. Now if I plug those in here, because they're all in the right units already, 15 joules would go on top. The 0.449 joules per gram degree C would go on the bottom, right? And then importantly, the mass also goes on the bottom of the fraction. Now, if we look at the units here, they're a little more complicated because we have stacked fractions, but joules here would cancel with joules there, and grams here would cancel with grams there. Now, degree C is on the bottom of one fraction that's on the bottom of the other fraction, which means it will be on top in the final units. So our final units here will be degrees C after we punch this in. So 15 divided by 0.449, right? And then divided by 12. That 12 is still on the bottom of the fraction. So 15 divided by this one, 15, and then that answer divided by 12. Be careful of that. A lot of people will actually multiply by 12 here And that means you've put 12 back on top. You could multiply these if you used extra parentheses around them, but that's just making your calculation more complicated. So it will work, but you're overcomplicating your calculation. Now, this gives me a temperature change of 2.78 degrees C. So we're not done here because we started at 28 and the temperature changed by 2.78, and that means we've got to add 28.0 degrees C plus 2.78 degrees C. That would be 30.78 degrees C. Now, because of the way that 28.0 was measured, we're limited to one place past the decimal, or the tenths place, so we should round this to 30.8 degrees C for our final temperature. We could call that T sub F. Okay, so we'll wrap the video there. We could talk a little bit more about sign there and what would happen if the temperature change was negative, and then the next example in the next video.